All right. Thank you. Yay. I wish I could be there in person or with everybody in person. All right, you should be seeing my slides. Look good? Okay, let's get it started then. All right, so I'm really excited to be here today. Let's talk about the case of the disappearing Martian atmosphere and how the climate has evolved over time. I'm Gina DiBraccio, as Connor said, the MAVEN project scientist, and I'm actively working with my team to solve this problem. We know that Mars was once a warm and wet planet with liquid water on the surface and a thick atmosphere. However, over the course of the planet's 4 billion year history, it's evolved to become a much different environment than the one that we see today. Today, we see a world that is dry and cold. This picture of the Mars surface, taken by the Curiosity rover, demonstrates how dry and rocky the planet is. But thanks to pictures like this, we also have evidence that water once existed on the surface of Mars. But what happened to the water and the atmosphere at Mars? The options are simple. The water could have gone down or up, down into the surface where the rovers can explore, or it could have gone up into space, being lost forever. To explore the up, we needed a spacecraft orbiting Mars in order to measure the atmosphere and how it's changing. And that's why we created NASA's MAVEN mission. It's exploring how much of the Martian atmosphere has been lost to space, not only over time, but today as well. MAVEN launched in November of 2013 and set out on a 10-month-long journey to Mars. It arrived in September of 2014 and went into orbit about the red planet. MAVEN's still orbiting Mars today, and we know that it can last until 2030. The MAVEN spacecraft has instruments on board that allow us to measure the solar environment near Mars, but also understand what's happening within the Martian atmosphere as well. And this means that we measure magnetic fields, charged particles from the sun and the planet, and even more. So there's three main questions that MAVEN is working to answer at Mars. It's what are the characteristics of the Martian atmosphere today? How much and how fast is the atmosphere escaping to space today? And how has this escape rate changed over time at Mars? So understanding how Mars has changed over time is pretty challenging. For example, we believe that Mars used to have a global magnetic field that shielded the planet from radiation coming from the sun, similar to what you see at Earth. But that's actually no longer the case for this global magnetic field at Mars. Instead, Mars has patches of magnetic fields across the surface called crustal fields. The crustal fields are fossils of a global field that once existed. And the blue arrows that you see here are measurements of the magnetic fields at Mars today. These crustal fields play an important role in shaping the space environment around Mars, called the magnetosphere. The magnetosphere is formed as the sun interacts with the atmosphere and the crustal fields at Mars, and the Martian magnetosphere is unique to our solar system. So in this movie, you can get a sense of how the magnetosphere is actually formed. Charged particles flowing from the sun directly interact with the Martian atmosphere in the regions where the magnetic field aren't able to protect it. And this interaction can strip the atmosphere away from Mars and leave it into space. So by examining data collected over several years at Mars, we can map different regions around the planet to understand how mass, energy, and momentum is transferred between the sun and Mars. And here you can see that the bright red region is where most of this transfer occurs. So the energy transfer dictates the regions where the atmosphere can escape to space. You can see in this movie that the colorful atmospheric particles of Mars are lost behind the planet in a region called the tail and upward in a space called the plume. We also monitor activity of the sun to understand how solar events change the rate of atmospheric escape at Mars. And we found that solar events significantly increase how fast particles leave. Right now, the sun is becoming very active, and we're observing more of these events. MAVEN can also measure characteristics of the Martian atmosphere by performing stellar occultations. And this works by tracking a distant star as we view it through the atmosphere. We observe how its wavelengths change based on the atmospheric particles that interfere with the starlight. And you're likely familiar with the northern lights or the aurora on Earth, but at Mars, we've also observed 3 different types of aurora, and these are created when energetic particles enter the atmosphere. This can occur along the crustal fields or not as well. So MAVEN has performed special observations to measure winds on Mars. We were able to measure the speed and the direction of these atmospheric winds, and we discovered that high altitude winds are actually disturbed by features on the surface like mountains or valleys. And in addition to science, we're supporting the new Perseverance rover by serving as a relay. As you can see here, when MAVEN flies above the rover, we collect its data from the surface, and we send it back to Earth for scientists like us to actually analyze. So MAVEN is continuing to explore atmospheric escape at Mars, and we've determined that a majority of the atmosphere has been lost to space. We're continuing to work to learn more about the climate of Mars and especially how it's evolved over time. Thank you.
Yay.
I'm just going to end the show so I can see people, but I'll keep this slide so that you can see that.
Great talk, Gina. Thanks so much.
Great.
Okay, so yeah, let's take some questions.
Chris, it looks like you have a question.
Yeah. If sometime in the future Mars were actually wrapped with a superconducting cable with a current through it to create a planet-scale magnet, could that give it a magnetic field strong enough to make a difference?
So there have actually been a lot of studies that people have done to try to figure out a way that there can be a magnetic field generated at Mars to protect the planet. And really, we haven't even figured out a way scientifically that that could be done. So I want to say the answer to your question is probably unlikely, but of course, the scientist in me says, let's do it in real life and figure it out. But for a lot of the thought experiments that we've done, it's proven to be very challenging to figure out a way to create that global magnetic field again.
Is that with today's technology or with the limits of physics?
I would say probably within the bounds of today's technology. But I don't know if anybody has actually sat down and tried to derive the different ways as well. Great question.
Like
Thank you.
it sounds like it would take a lot of energy to do that.
Yeah, for sure.
If it's superconducting, you only have to charge it up once.
Good point.
Yeah, that's true.
Renata,
are you a physicist?
No, but I read a lot.
Cool.
Oh, hey, thanks for the presentation. That was really awesome. Really great visual stuff. So my question is also kind of about technology, but it's kind of more about like the lifetime of technology. So you said this mission was launched in, was it 2013 or 2003 or?
2013.
2013. So when you launch a mission like that, how do you future-proof the technology so that by the time we're starting to get stuff back, then we haven't developed new technology that makes it obsolete by the time we're using it?
Yeah, so for exploring space, one big thing that we look at is the heritage of our spacecraft and our instruments. So how long have they, actually been working as far as technology is concerned, and have they flown in space before? So I would admittedly say some of the things that we're flying in space isn't the newest, breaking technology, because that's risky. And at least from NASA's standpoint, we are very risk adverse because we want our things to work when they go to space. But sometimes we do experiments and technology demonstrations to say, this is high risk, but if we can have this instrument, successfully measure data, that would be great. So a lot of the hardware that we send into space is, it has history behind it, right? It's, for example, the magnetometers that I work on that measure the magnetic fields in space. We've been flying this type of magnetometer since like the 50s. So it's not a new technology, but it's a robust technology. And as far as having it last in space, NASA has us put estimates and limits on how long it can last. And so, of course, we're very conservative with that. For instance, MAVEN's original primary mission was only supposed to last for, I believe, a year or two. And here we are, 6-7 years later, and now we're telling you we can last until at least 2030. And at that point, so far, our instruments have barely degraded. They're doing really well. And by the time 2030 rolls around, we still could take those measurements. The problem is we'll run out of fuel at that point. So it's a fuel standpoint rather than having our spacecraft and our instruments be able to survive. So That's why, pairing with the private industry is a lot of fun because they have the freedom of pushing the envelope of technology-wise a little bit more.
Very cool. Thank you.
Irving, did you have a question?
Sorry, I don't know how to raise my hand in Zoom. I'm used to using something else, but I had a question, technical question about the atmosphere of Mars. So like Mars has, I guess, maybe we would say a residual atmosphere, but actually is this atmosphere kind of just in equilibrium with the polar ice caps? Like, you sublimate a little ice cap and then you lose it to space and then you sublimate a little ice cap, or would you say that it's a sort of more like a persistent atmosphere? That's not a very well-formed question, but maybe you could speak to that.
Well, that's a great question. And I might actually punt it to one of my colleagues here who knows more about the atmosphere. Because for me, from my standpoint, I care about how the atmosphere is lost, not how it's generated. But you're right. I mean, obviously, it has to be generated in order to have something to lose. So part of that is, a water cycle that used to exist and or exist to a certain degree. For me, I look at what physics and energy can enter into the atmosphere to excite it. So if Giuliano, not to put you on the spot, but if you have an answer to the question, that would be great. You're the atmosphere expert here.
I can jump in on this question at least. No, it's by the way, great question, because we're exploring these things in detail only right now, actually. And one of the things we discovered, for example, in last months, is that when in the summer, the South Pole starts to get heated, that water that sublimates from the pole rises up to incredibly high altitude, 100 kilometers. And from there, it escapes the atmosphere very easily. So that might be actually a seasonal phenomenon, and it could happen, yes. So the water cycle and the water escape can be intimately related in a way.
So it looked like Irving had a question, and then we'll go to Mel after that. Oh, sorry, did someone?
Oh, no, I just wanted to chime in just that, but it is an atmosphere. It's not like a tenuous atmosphere. It's a legitimate atmosphere. It's just very thin.
But then when you compare it to a planet like Mercury, it feels as if it's a very thick atmosphere.
Forgive me, Barbara, do you still have a question? You're on mute.
I was going to ask if we know from the findings what the atmosphere is composed of.
Yes, not to spoil Giuliano's talk coming up, but he has a really nice slide to describe that. So okay. I'll pause for his slide, okay. But yes.
Looking forward to hearing that.
And this might be the last question. Mel, if you still have a question, go ahead.
Hey, this is kind of like a technicality, nuts and bolts question, but you mentioned, of course, you're supporting the rover right now in sending data. How do you guys coordinate that? How much data can you send back every day? Like, what does that look like, just from a kind of like a logistics point of view? I'm just curious, because I know it is a fairly thin pipe, and you could probably only broadcast for a certain amount of time with a certain amount of battery power. How do you guys negotiate that?
Yeah, that is a great question. And I can get you the number about how much data we send back, per day or whatnot, if I can cheat while the other talks are going on and look it up, because our engineers are the ones that plan that. But yeah, I mean, first of all, we practiced a lot because not only are we relaying the data back from the rover on the surface now, but we also supported the landing of the rover. We call it EDL, entry, descent, and landing. And so while Perseverance was landing on the surface of Mars, Maven was watching and sending back the data just to say, how is it going and what's going on. And so in order to coordinate that and in order to be able to fly over top of the right location, grab the data from the rover and then send it back to Mars, we were practicing for a very long time with the other rovers, with Curiosity rover, which Jen will talk about, and also with the InSight lander as well. And so right now, Maven orbits Mars, I would say it's around 6 or 7 times per day. And we are serving as a relay asset about 3 of those times. So it becomes kind of a tug of war of we're sending back data from Perseverance, but we also have our own data to send back because we continue to collect data even when we're grabbing it from the rovers. And at that point, we have to sacrifice a little bit of the Maven data so that we can make room for the rovers. But we're comparing, data from the surface to the atmosphere. And so we've created this entire Mars structure that is a lot of fun to deal with. But there's a lot of coordination. Thanks to our team of engineers, it's been successful. And I can take a sneak peek at the data rates and how large those data files are, if that helps. And I can get back to you at the end of it.
Cool, thanks. No, just curious.
Great, yeah.
Woo! Yay! Thank you, Gina.
Thank you. I'll stop sharing.